Weather Change by Sean Quigley, Thomas Wilmey, Taylor Yee, and Aidan Hadley. Our objective. Our objective, Why Weather Changes, is an informational lesson that will teach you about how weather works and changes. Our weather-headed lesson will be focusing on the big picture of why weather changes. During this video, we will cover the history and evolution of weather instruments and the knowledge about forecasting, also about the processes of wind and thermal energy transfer. While we cover these concepts and even more, we will provide detailed slides and models to help portray the overall concepts. Now, sit back and get ready to learn. Here's some iQuest vocab that will be reoccurring in our lesson today. Atmosphere. Atmosphere is the envelope of gases that surround Earth and any other planets. All weather we experience happens in the troposphere, the lowest layer of the atmosphere. Precipitation. Precipitation is the condensation of clouds, so it's any rain, sleet, snow, hail falling from the sky. Molecules. So molecules are groups of atoms bonded together, too small for us to see. They are the smallest fundamental unit of life. The smallest fundamental unit of a chemical compound that can take part in a chemical reaction. And these molecules make up most of things in matter. So convection is a really big part in air's movement and flow. So convection deals with thermal energy in fluids, not solids, so that's meaning water and air, but today we're just focusing on air. So when the hotter, thus less dense air rises, and cooler, thus denser air sinks under the influence of gravity. And this consequently results in heat transfer. So temperature is the degree or intensity of heat. It is not heat itself. So temperature is perceived by touch and by thermometers. So when you're feeling cold or feeling hot, that is heat, but the intensity or degree is lower sometimes than others. Energy. Energy is the ability to do work. There is potential, stored energy, and kinetic, working energy. Energy. Potential energy is the stored energy in an object, whereas kinetic energy is the energy a body possesses due to its motion. There's a heat transfer. There's heat energy, heat energy, which is thermal energy, radiant energy, mechanical energy, electrical energy, chemical energy, and nuclear energy. And they all fall under potential and kinetic energy, the two large classifications. Thermal energy is the energy that comes from heat. Thermal energy is made by the movement of tiny particles or the air molecules within a object or substance. The faster the tiny particles or molecules move, the more thermal energy there is. Alright, here's a little bit more. So matter. Matter is anything that has a resting mass. It's any physical substance. It's anything that has mass and takes up space. It is distinct from imagination in minds, and it is distinct from energy. Density is the degree of compactness of a substance in a specific area. So how many things are in a specific area? There are 4 states of matter that matter take on: solid, gas, plasma, and air. So evaporation is really important with making clouds, and the water cycle. You see, evaporation is when liquid turns into a vapor, and and when this happens, the vapor rises into the air onto the next process, which is condensation. Condensation is when that water vapor condenses and becomes and condensation is responsible for the formation of clouds. So from water vapor, it condenses in the clouds, and it condenses into precipitation, which is like rain. In conduction is weather. Conduction is when heat is directly transmitted through a substance when there is a temperature difference between the adjoining region without the material moving. like in our Crisco globs lab, where the heat transferred through the metal to the Crisco globs, which they're then then heated and fell off because they melted. But because the atmosphere is not a good conductor of heat, we will not be mentioning this vocab word much throughout the video. Here is a timeline of the evolution of instruments and understanding of weather. So here, if you can, all right, there we go. So here in the 1400s, Leonardo da Vinci created the hygrometer. The hygrometer measures the humidity in the air. After that, Galileo Galilei invented the thermoscope, which displayed the change in temperature in 1593. Down here, we have Italian physicist Evangelist Torricelli. He created the barometer in 1643. The barometer measures air pressure. Here we have Ulf Christian Romer. He added a temperature scale to the thermoscope that Galileo created, and that created the thermometer in 1701. Here, the telegraph was born, and that created the modern age of weather forecasting in 1835, because without the photograph we wouldn't be able to make our maps, and we would be less developed in our understanding of weather. Then next we have Fitzroy. Fitzroy published a weather book, a book called The Weather Book, that advanced the scientific opinion of meteorology in 1870. Here, in 1896, a book called The International Cloud Atlas was published by Hugo Hildebrandsson, my bad. Sorry. And then next in history, we have Wilhelm Bjerknes working on making a physical-based way to forecast weather in 1904. And as you can see so far, there's a pattern of the evolution of instruments and the evolution of understanding of meteorology and the skies and weather. Next, we have the radiosonde. That was invented to take measurements at high altitudes in 1920. And then the first public radio weather forecast was made in Boston by Edward B. Rideout, 1925. Very important. Very cool, too. You see, the first televised weather forecast with weather maps was produced on BBC in 1936. Hope you guys can see this. Okay, down here. The first television and infrared observation satellite, Tyros 1, the polar orbiting satellite, was launched in 1960. The first geostationary operational environmental satellite was launched into orbit in 1975. Then over here, the Weather Channel began broadcasting 24-hour cable network in the U.S. 1982. Another big leap into our modern era. Down here, the U.S. started a $4.5 billion modernization of the National Weather System in 1989. Very big step. And then lastly, for this timeline, the U.S. Doppler radar network was fully developed in 1997. Okay, here are clouds. You see, clouds throughout history have always been imaginative, misunderstood. But with the help of Luke Howard around the 1800s and before, while he was a schoolboy, he would observe the clouds, and he eventually created 3 main classifications of clouds. He did end up making 4 more crossbreeds of them, and today there are now 3 more crossbreeds. So he came to he created the category cirrus clouds. Cirrus is Latin for tendril or hair, so that's what the clouds look like. Cumulus clouds. Cumulus is Latin for a heap or pile, also what they look like. And lastly, stratus clouds, Latin for layer or sheet. So without his research and breakthroughs, there'd be a lot less understanding of the skies, of clouds, of precipitation, of all these processes, because clouds kind of tie together everything in a way. They're really important, and thanks to him, we know a lot today. Great guy. Key concepts. Here are some key concepts that we've learned throughout this throughout this unit. One of the biggest things we came over, we saw it a lot, we answered a lot, it's why weather changes. And throughout this video, we're answering it in many ways, showing you why, but here's like a quick sum up. So weather is always changing. Even if you can't tell, some feature is probably varying from what it was a second ago. And one of the element that might be changing is one of the 6 elements of weather, which is air temperature, air humidity, air pressure, winds, cloudiness, and precipitation. Okay, nephrology, it's not up here, but nephrology is the study of clouds, but more important is meteorology, which is the study of weather. Meteorologists study meteorology in an attempt to predict future weather conditions. They are a weather forecaster. Weather, for us that do not really study it on a daily basis, meteorologists are very helpful on our handy services like King 5, etc. Climate differs from weather because weather is the specific conditions, whereas climate is the overall conditions over a long period of time. And then again with the classification of clouds. Alright, here are the big questions we'll answer in the next few slides. I will read them. I'll read them right now, and then we'll go over them throughout the next slides. So, how do places become humid? How is air heated? What are the patterns of wind? How are hurricanes formed? How are tsunamis created? How are tornadoes formed? How does lightning in a lightning storm occur? Let's get started. Alright, how do places become humidity? You need to first understand and know what humidity is. Humidity is the amount of water vapor in the atmosphere or atmospheric moisture. This atmospheric moisture is caused by sun's heat. The sun's heat causes water to evaporate. Back to that word, very important vocabulary. It causes it to evaporate into water vapor. The water vapor is in the air, and that is humidity. But here, listen to this. The more thermal energy the air has, the more spread out the air molecules are, thus supplying more room for water vapor. So that, therefore, the more humid the area is. There can possibly be too much humidity in an area, but let's hope you don't find yourself in that situation. And the more humid a place is, the more amount of water vapor there is, and this has to do a lot with evaporation, really important. Also with thermal energy. How is air heated? This is one of our main concepts this year, about how air is heated. So, first and foremost, Earth's atmosphere is heated by the sun, obviously. Earth is able to absorb and trap or hold onto the sun's radiation. This is called the greenhouse gas effect. The greenhouse effect. Our atmosphere is able to keep and hold the heat. This really helps at nighttime because the radiation isn't reaching that area, but there is still heat. It is not below freezing. It's not incredibly cold. But in some areas it is, but for the most part, no. Um, Also, the heated up surface of Earth, um, the touching air to the surface also heats up the atmosphere. And another thing is Earth's rotation um, is actually really good because an area isn't exposed for too long, and that creates a really good inhabitable planet. What are patterns of wind? So wind isn't just a small thing. There's actually a broad concept, broad patterns, really big. You see, okay, wind wind is formed by the differences in air pressure. And the greater the differences in air pressure, or the closer the two bodies of air are to each other, the stronger the wind is. Um, okay, wind is a massive part of our weather system. It moves weather around, very important. Okay, the pattern of rising and falling air is a convection cell. Um, when the air cools and travels toward the high pressure areas, that is a downdraft, vice versa for an updraft. That is still part of the convection cell. So the air replaces the air that just left, and thus creating wind, and that also has to do with difference in air pressure. Okay, in Earth's rotation, curves the path of the wind, either east or west. This is called the Coriolis effect. I find it really neat how that does that. How the rotation does that. All right, here are the three types of wind: the polar easterlies, which are easterly winds coming in from the poles. Prevailing westerlies are westerly winds that are in a heading northeast away in the middle latitudes. Just to help you picture this, it's heading away from the equator, but it is not at the equator. But then the trade winds are easterly winds which travel into the equator. Will travel towards the equator, my bad. Alright, wind continued. So air masses are large bodies of air with the same temperature and water vapor levels throughout. So the U.S. has 4 major air masses, and when they collide, a front is made. A front is a boundary where 2 air masses meet and weather occurs. There are cold fronts and warm fronts. Cold fronts is when a cold air mass collides into a warm air mass and pushes the warm air mass up, creating cumulus clouds, and heavier weather occurs due to this. And then a warm front is when the warm air mass catches up with the cold air mass and slowly goes over it, creating thin, long stratus clouds, and the weather is less intense than a cold front. So that's fronts, but then the 4 types of air masses, they are called the continental polar, maritime tropical, and continental tropical. How are hurricanes formed? Hurricanes are the most violent storms on Earth. They're terrifying. So hurricanes are like cyclones and typhoons. However, it's called a hurricane because of its position, the Caribbean and Atlantic. That's where it's made. They're all tropical cyclones. They're all the same, made the same. It's just their position on Earth. This is how they're made. They have a system of clouds and warm, moist air, and the warm, moist air rising, and new air taking its place, which is convection. So you have the system of clouds and wind spins that are fed by the heat and water evaporating from the water surface. And as the system spins faster and faster, an eye forms in the middle, and the eye is much calmer and has very low air pressure, while higher air pressure air comes in down into the eye. These storms are highly destructive, leaving little behind on their path. No remorse. How are tsunamis created? Okay, if you're afraid of water, tsunamis are very scary indeed. Tsunamis are a series of waves that are created due to large disturbance, such as an earthquake, landslide, volcanic eruption, or meteorite impact. Underwater earthquakes occur at the boundaries where tectonic plates meet. This causes the water to move up or down and under the influence of gravity. Okay, the water tries to find a stable position again. That's why it does waves, because it's trying to balance out. This also happens in undersea landslides. They can create that ripple that you would see with earthquakes, and these landslides can be triggered by large earthquakes. Undersea volcanic eruptions, the upwards motion can create a wave that will eventually become a terrifying tsunami. And also, asteroid meteorite impacts, very unlikely. Hasn't happened recently that I know of, but that is definitely a possibility. Okay, tsunamis can be very tall and destructive, or they can be short but really long and destructive as well. But they both have terrible impacts. All right, tornadoes. Very interesting event indeed. Okay, tornadoes. Tornadoes are a destructive vortex of extremely high winds that are a funnel-shaped cloud. Tornadoes are formed inside of storms and connect to the ground with a funnel of cloud. Tornadoes begin with a thunderstorm that are especially big and powerful. These big thunderstorms are called supercells. For tornadoes to form, there has to be a very specific condition. There has to be rising air. Any storm is formed by condensation. The clouds form by condensation and evaporation. The condensation lets off heat, and that heat powers the huge upward drafts of air. And the more powerful the storm and more condensation, the more powerful these updrafts become. Alright, these updrafts are important because they help shape the tornado if it gets to that level. If there's a lot of moisture in the air, a base cloud or a cloud base develops, and that will eventually help feed the tornado if it gets to that point. Okay, so when all the conditions are just right, a vortex of air can form that is enclosed by the storm. And when a wide and tall tube of spinning air then gets pulled upwards, a mesocyclone is formed, and cool, dry, sinking air begins to form around the backside of the mesocyclone. So mesocyclones are kind of like tornadoes, but they're not on the ground. Lastly, the bottom begins to become smaller, increasing the speed of the wind, and if it takes that bottom moisture level, it can turn it into a rotating wall of cloud. Scary. Once the tube of spinning air touches the ground, it becomes a tornado. How does lightning in a lightning storm occur? For lightning to be created, warm and cold air is needed. When they meet, the warm air rises and creates thunderstorm clouds. This is a cold front. The water vapor from the warm air and crystals from the cold air collide and knock electrons off, which creates static electrical charges in the storm. The top of the storm cloud has positive charges, whereas the bottom has negative charges. When the negative charge is strong enough, the cloud will let out energy, and it will go to the positive charge, and then a lightning bolt will form, and the lightning bolt will heat up the air around it because it is approximately 6 times the heat of the temperature of the surface of the sun. Excruciatingly hot. And that is the flash we see, but then the thunder is the wave of air that it creates because it makes the air spread quickly around it. Energy conversion in a storm. So energy conversion is the change from one form of energy to another. So first things first, energy conversion is when I just mentioned that. This isn't just kinetic energy to potential energy or the other way around. This has to do with all the energy that lies between those two categories. A storm is composed heavily of moisture because of the clouds. Thermal energy created those clouds. Thermal energy creates evaporation, and then those clouds are made because of condensation. And then the rising and falling air, which is convection. Also, the liquid turning into water vapor is evaporation. Then it condenses and forms clouds, which hold the moisture. So what I'm saying here is there's thermal energy that creates the evaporation, and then the evaporation creates clouds, and then this creates wind. The convection creates wind, and wind is mechanical energy, so it's from thermal energy to mechanical energy. And then I can dig deeper, go further. So, okay, this mechanical energy can change into electrical energy or lightning. So the wind, when the ice, or well, colder particles of water in, like maybe the ice crystals and the regular just water vapor collide, they knock electrons off and create that positive negative charge I was talking about earlier. So this is how it turns from mechanical energy to electrical energy. These are just a few examples. There are definitely more. Alright, here's a little diagram I made of Babylonians and in 600 BC and of our weather forecasting in 2016. Try to make this brighter. Sorry about that. Alright, okay, in 600 BC, Babylonians used clouds to predict the weather patterns. And this is like the earliest form of meteorology. Whereas today, we have weather satellites that display the weather on a map. So meteorologists, they use these to help predict weather, which is their job. But then maps like these are given color to help the clouds stand out better and make them easier to understand. But as you can see, on this hand, we have early, just only observations, but here we have more scientific observations with more instruments as satellites. So that's kind of shows you the evolution of meteorology and understanding of weather. Because for them, they don't understand weather. They just know that the clouds are there. Now we understand weather and we know what it is, but there's still a lot to learn. All right. Here's the water cycle, a really important feature of weather. Here's a little diagram showing the collection of water, evaporation, condensation to clouds, and then precipitation. Alright, so the water cycle is a huge part of our weather. It involves many large concepts such as evaporation, precipitation, collection, condensation, clouds, and heat. A heat source like the sun heats up the collection of water, like the ocean, and the ocean is the largest contributor to clouds and the water process. And water vapor, it rises because of evaporation, and then it condenses because of condensation into clouds. Those clouds eventually get too heavy to hold all of that water, and they let that go as precipitation. And then that goes back down into the main collection to go through the process all again. Without this process, there would be no rain and clouds. There would just be collections of water, and the water sources would be a lot larger. There would be much drier lands and fewer plants. I'm saying this to help portray the importance of the process better. Okay, so density of air. With the thermal energy, the farther the molecules are apart, the less dense it is. The closer the molecules are apart, the closer the molecules are to each other, the more dense it is. This is cold air and hot air. Cold air is the more dense, and hot air is the less dense. So let's say you have 1 cubic feet of hot air and 1 cubic feet of cold air. The resting mass is going to be greater for the cold air because the molecules are closer together. That's just to help visualize it. And so hot air has more energy and it's less dense. The molecules are moving faster too. And in cold air, the molecules are moving slower. Density of air is part of convection, and yes, that is cool. Alright, here's a convection cell. Here's a little diagram if you can see it. It's hot air rising, cold air falling. Alright, okay. So, a convection cell is a process of hot air rising and cold air sinking. So the cold high pressure air moves toward the hot low pressure air, creating this circular motion we know as a convection cell. This deals with density too and thermal energy. All this stuff deals with this. The greater the difference between these high and low air pressures, or the shorter the distance, the faster the wind will blow. This creates wind. Air pressure is the weight of the air weighing down on us, and this has to do with the compactness of density. Oh, whoopsies. Here is the last slide. Okay, here's a summary of what we've done. Throughout this weather unit, we have learned and studied about how Earth's atmosphere is heated, how wind is made, patterns of wind, how convection and conduction work, how different types of storms are made, and how the patterns of wind. Back to the main idea: why weather changes. You should not now know that it changes because there are many processes and occurrences that are limited to our environment and that are ever changing. Because all the factors, there's many things that change them. They're never the same. But then, so therefore, because these features are always changing, therefore weather changes. These features are why weather changes. These concepts are these concepts that we have covered today in our video, and are what we cover. Okay, so these concepts are what we have covered today in the video, and we hope that we have introduced cool new information to you about our weather system, how our weather system works and changes. Thank you for listening. Yay.